All right. I think you heard me the first time, so I'll skip that introduction there. So basically, we're going to do some basic science on radiation and radiation safety. So let's just continue on. What is radiation? Did we lose this? Hello? Can you hear me?
So we can hear. We can, if it
Okay.
won't work, it might be out of batteries. So I'm
All
sorry
right.
if it's out of batteries.
So what is radiation? This radiation is a spontaneous decomposition of an unstable nucleus into a more stable nucleus. Anytime there's a nucleus that is unstable, it can be unstable because of increased energy, increased mass, increased charge, or a combination. So in essence, it has some kind of structural flaw, and it's unstable that way. And it tries to get back to stability by eliminating these flaws. So in the process of eliminating these flaws, you can send out a particle, a radiation, or a combination of the two. So that's what radiation is and what radioactive decay is. So there's four main types of radiation that we're going to be talking about: alpha radiation, beta, gamma, and X-ray radiation, as well as positron emission. So how did they name this alpha, beta, and gamma? Well, Madame Curie, when she was doing her experiments with radioactive radium, she put this radioactive element into a magnetic field and as well as an electric field and imaged the resulting emissions on a photographic plate. And what she found was that there was three distinct populations of discoloration on the radiographic plate. One did not change direction at all from the source. The other was deflected to one side, and the last was deflected to the opposite side. So she knew that there was one that did not have charge, one that did have a positive charge, and one that did have a negative charge. So that she named them alpha, beta, and gamma. So that's how we get our alpha, beta, and gamma radiation. The line of stability is pretty much the increasing number of elements in the periodic table, the mass number. There is a line where the atoms will be stable, and around it there will be an area of atoms that are typically unstable, and we'll try to get back to that line of stability. And so if this blue line is the line of stability here, everything above that blue line will try to become more stable because they have excess neutrons, they will try to get more stable by losing that neutron. And on this side, below the line of stability, it's usually they have excess protons. So they will try to get rid of the excess neutrons by beta emission, and they will try to get rid of the excess protons by alpha and positron or electron capture. So that's how the atoms try to get back to the line of stability. Excess neutrons is beta emission, excess protons, alpha, electron capture, and positron emission. And in the case of excess energy, it just releases energy from the nucleus without any change in the atomic structure. So excess neutrons, basically how the atom tries to get back to the line of stability is it makes the neutron into a proton. So there becomes a net positive charge inside the atom. And when that happens, the atom has to eject a negative charge. So that is a beta particle. The beta particle is ejected out from the nucleus. The net result is that the atom becomes more positively charged. And so you have basically an electron that is emitted from the nucleus of the atom. And the most common one that we use in medical medicine is I-131, which is a beta emitter. For alpha emissions, those that have excess protons, the best way to get rid of excess protons is by alpha emission. So alpha emission is basically a helium nucleus, 2 protons, 2 neutrons, and they get ejected from the nucleus. And the atom becomes smaller in size. It gets rid of 2 positive charges and 2 neutrons. We used to not have any alpha emitters in medicine, but there's recent edition of radium-223, actually, which we use for treatment of prostate cancer. That's just been approved last year. So radium-223 is an alpha emitter that we use for metastatic prostate cancer. Radium-226 used to be on the radioactive watch dials that would make the watches glow. That's a whole different story. Radon and polonium also are alpha emission. You remember polonium by the poison that was used on the Soviet dissident by the Russians about 10 years ago. So alpha emitters have been used in different places, so just remember that. Excess protons, beta plus is different than beta minus. Beta plus is a positron. It is a positively charged electron that comes out from the nucleus. So basically, the excess proton, the proton becomes a neutron inside, and the positive charge is emitted from the nucleus, and that's a positron emission. And our main one that we use for positron emission is F18 FDG for our PET tracers, and also rubidium PET for cardiac PET. Electron capture is also for electron excess protons. Here, there's a net positive charge in the nucleus, and what happens is the closest inner shell electron falls into the nucleus, and it converts one proton into a neutron. So the net charge becomes less by one, and there's a loss of an electron from the inner shell. And what happens subsequently is that the outer shell electrons start falling into the inner shell to fill that. When that happens, they have to release excess energy, and that is released in the form of an X-ray. The main one that we use in medicine is thallium. Thallium decays by electron capture, and we use the mercury X-rays of thallium to image our patients. Photon emission, that's just excess energy inside the nucleus. The nucleus becomes more stable by just releasing that energy, and that's usually in the form of a gamma ray. There is no difference between a gamma ray and an X-ray except for the origin of where they're coming from. The gamma rays usually come from the nucleus, and they can be very energetic. The X-rays come from the electron shell as they fall into a lower energy orbit. And those usually are much less energetic than the gamma rays, but the characteristics of both of these radiations are pretty much identical. Something else that you need to know is Compton scatter. Compton scatter basically is the interaction of the photon with any matter that interacts with it. How it affects our cameras, our imaging, is that if we put a point source inside the camera, we get a nice photo peak, say of technetium. You see the photo peak right here. Nice clean photo peak, and then you have different smaller photo peaks for different energies below that. When we put that same radioactive tracer inside a person, you have this huge bump of scatter, backscatter. So all that's the photons interacting with matter inside the body before it gets to the camera. And that's what happens, and that's what causes a lot of our blurring on our camera systems. So that's what Compton scatter is about. The other thing you need to know about is BREMSSTRAHLUNG radiation. BREMSSTRAHLUNG is German for breaking radiation. So what happens is when a photon comes in close proximity to an atom, it will bend around the atom and go in a different direction. And as it does so, it slows down. And when it slows down, it has to release energy. So that energy is released usually in the form of an X-ray. So that's what BREMSSTRAHLUNG radiation is. What's important about BREMSSTRAHLUNG is it usually happens with electrons. And so electrons, a type of electron is beta particles. So when you use beta particles like iodine-131, you really don't want to use lead or any type of metallic shield, because what's going to happen is that, what's going to happen is that that's going to interact with the metallic atoms and create X-rays on the other side. So your shield is actually, your syringe shield is actually going to produce more radiation than you would get with a lower Z particle shield like plexiglass. So for beta particles, you typically want to use plexiglass or something that has low atomic number. The same thing happens in an X-ray tube. The electrons are shot through to a target, and as it slows down near the atom, it produces X-rays. So that's one of the two methods by which X-rays are produced inside an X-ray tube. The other thing that you need to know is characteristic X-rays. How does this happen is when a speeding electron actually collides with the electrons surrounding the tungsten atom, any atom. And as the electron collides with the orbital electrons, that electron is ejected out. The outer shell electrons start cascading in, and then you get X-rays that are produced from that. So this is what's known as characteristic X-rays. And that's typically how we get X-rays from an X-ray tube. The electrons are shot from the negative end through a gap at the tungsten target right here. As it hits the tungsten target, the X-rays are produced, and that's how we get X-rays from an X-ray tube. So the two main methods that produce radiation inside an X-ray tube are the characteristic X-rays and also BREMSSTRAHLUNG. Other things you need to know: ALARA. Everybody's familiar with ALARA pretty much. It means as low as reasonably achievable. So basically, it's the extra things you do to reduce radiation. Okay, so that's one of the guiding concepts in radiation. So you have to always know about ALARA. So what are the concepts? They include minimize time, maximize distance, maximize shielding, and minimize contamination. So how do you reduce time? You manage your work area efficiently. If you're doing interventional or hard cats or whatever, get off that pedal as much as you can. Use your last minute hold, those kind of things. Anything to reduce the time of radiation is very good for ALARA. Again, avoid redundant views, ensuring correct patient positioning prior to imaging, exposing the patient only when viewing the TV image, and awareness of the 5-minute notifications when the machine will beep every 5 minutes to let you know that, okay, you've crossed 5 minutes of radiation, etc. 5-minute alarms, last minute hold, pulse fluoroscopy, boost modes only for heavy patients. So just all those things will help reduce the radiation. Distance, remember the inverse square law. The radiation is reduced by the square of the distance. So if you move twice as far away, the radiation will be reduced by 1/4. So if you're just 2 steps away, that'll reduce a lot of radiation to you than if you're much closer to the radiation source. Shielding, always put your attendings in front of you, so that way they block the X-rays, okay? Other things, wear leaded aprons, make sure they're double-sided, never turn your back to the radiation beam, use leaded gloves, use leaded glasses. Remember, there is a lot of increased cataracts in cardiologists and interventionalists. So leaded glasses are very important if you want to go to that field. Another concept is half-value layer. How do we measure the effectiveness of a shield? It's by half-value layer, basically. So it is the amount of thickness of a material to reduce the radiation by 1/2. So the half-value layer of technetium, which has 140 keV photon, is about 0.025 centimeters of lead. Now the half-value layer can be different for different materials. So in lead it's 0.25. For aluminum it's 1.79 centimeters of aluminum for the same technetium agent. For a more energetic agent, also like F18, That's a gamma ray. It's 511 keV versus 140 keV. You need a lot more lead shielding to do the same thing as for a technetium. So just remember the half value layer, that concept is important when you're talking about shielding. Penetration of matter, just remember the alpha particle is probably
Can I
the...
ask you a question?
Sure.
So after you held it, after you put the shield on, right?
Yes.
And then you're still getting 50% of the radiation?
If it's one half value layer. It may be 2 or 3 half value layers. So it depends. You put a shield on, you purchase a shield, the company will tell you, okay, this is equivalent to 0.25 centimeters of lead. Okay, and then you have to just know how much that reduces it by. So
The ones that we use like everywhere, like here or at the VA,
Mhm.
do you think they're protecting us? from-
yeah, at least about 90%. So there's always going to be some that's going to penetrate through. And remember, your lead is protecting here. Your eyeglass is protecting here. Nothing protects you here. Hopefully you'll have a thyroid collar on. Hopefully you'll have a leaded mask on. So there are areas in your skin that will be getting radiation, okay? And luckily you're not in the primary beam. You're getting scattered. So the primary beam is not hitting you. It's just a scatter that's coming off the patient and the table. So those things are very important to understand. But know that you will be getting radiation. That's why ALARA is so important. It's not just shielding. It's timing, it's distance, it's everything, okay? It's the whole concept together to make this radiation safety.
Only the strong cells survive these, so technically we're stronger. Yeah, it's one
Yes, we'll talk about that in a second. So alpha particles are the most destructive. It's +2 charge, but it can't even get past your skin. So it can't produce much damage to you unless you've internalized it. Beta particles can get through your skin, but can be stopped by aluminum, whereas gammas and X-rays can get through aluminum, even some concrete, and are usually stopped by lead. So just remember those are the penetrative powers of the agents, but the most destructive, if they're inside you, will be the alphas and the betas. So units of radiation, just understand some of this. The becquerel is a unit of reactivity in the SI units. It's 1 decay per second. The Curie is equal to 37 gigabecquerels. The gray is a unit of absorbed dose for ionizing radiation. And you can read about this later, but we'll go through this again. So starting with nuclear medicine, just something about the basics of nuclear medicine, how the camera works. So typically what happens in a nuclear medicine camera, the patient sits below the camera down here. The photons come out from the patient and go through what's known as the collimator to help align the photons. And it strikes a scintillation crystal where interaction with the crystal creates a spark or a scintillation. That scintillation is picked up by what's known as photomultiplier tubes, which then go to a positional logic summing computer, then a pulse eye analyzer, and then the finalized image is sent to the monitor. So what does the collimator do? The collimator will block any incident photons arriving at a sharp angle so that you will see only true photons coming straight to the camera. That helps to clarify the image a lot better. The sparks are created. The crystal itself is the heart of the nuclear medicine camera. This is made out of sodium iodide. And the sodium iodide has some thallium impregnated into it, and it's the thallium that actually converts the light, creates the light from the X-ray. So this is what happens. The photon comes in, hits the sodium iodide, the iodine electron breaks off, hits the thallium, and that creates the scintillation. So really weird stuff that's happening inside the scintillation crystal. So once that happens, it gets into the photomultiplier tube. Inside the photomultiplier tube, the photon comes in and it gets converted into electrical pulse. The electrical pulse is then amplified through diodes to the point that it actually creates a charge that the computer can pick up. And the positioning and logic circuit, say the spark happens at this one point. These are photomultiplier tubes. So these 3 photomultiplier tubes, or PMTs, will create an electrical charge, and based on how much electrical charge each one is sending off, the computer can know exactly where that spark happened. The pulse height analyzer, if we're using technetium, the spark is proportional to the energy of the photon. So if the PMTs send out a signal that's equivalent to 140 keV, the computer will accept that. If it sends a signal that's too high, above a certain window, those are rejected, as well as energies that are too low. So it'll only choose a certain energy window inside all the sparks to say, okay, these are true photons that we can accept. This is the photo peak that we typically use, around a 140 keV photon for technetium. We'll go down to 126 and 154 as the high end. That's a 20% window around the photo peak. If that photo peak is adjusted too low or too high, you get a real measly looking pattern, because the PMT tubes start to show out incorrectly on those. Okay, so we have to make sure that we're windowing correctly to the agent that we're imaging. All right, we talked about that. Effects of ionizing radiation. So what happens when we deal with radiation? Damage to a cell can come from different direct or indirect actions. In direct cell damage, what happens is the actual photon or the particle will actually interact with the DNA or cell wall, and the cell either has a severe injury that it dies, or it repairs itself and becomes a different kind of cell, possibly even a cancerous one. Indirect cell damage occurs when radiation interacts with the main molecule that's in your body, which is water, and converts that into free radicals, and those radicals cause damage to the body. So that's a simple explanation for that. For low levels of radiation exposure, the biological effects are so small they may not be detected even. The body repairs many types of radiation and chemical damage. The types of biological effects from radiation are 3 types. You can cells experience DNA damage and are able to detect and repair the damage. They can experience DNA damage and are unable to repair the damage. These go through programmed cell death or apoptosis, or the cells experience non-lethal DNA mutations and then become other cells. People typically survive exposures to moderate doses of radiation. Symptoms whose severity and duration depend on the dose. So extensive experiments, of course, haven't been done on anybody, but we do have data from Hiroshima and certain accidents that have happened, like Chernobyl and different accidents around the world. LD50 is a concept that you should know about for all drugs and all that. Radiation also has an LD50. So there's an LD50-30, which means a lethal dose for 50% of exposed population to die within 30 days of exposure. And that's about 4.5 gray or 450 rads for the whole body exposure. Death of the person may result from overall insult to the body or from destruction of a vital organ. The acute exposure is much more important than the chronic exposure. If you get a big dose acutely, it's going to be much more toxic to the body than a long, prolonged, lesser dose. Again, radiation hormesis. So what is radiation hormesis? It's a theory that ionizing radiation is benign at low levels. The exposure and doses at that level of natural background radiation can be beneficial, and it's also explains why there is individual variations in a lot of things. Numbers of studies support this theory that low doses of radiation are benign. This is just a graph of the two models that are out there. One is the radiation hormesis, and one is what's known as a linear no threshold. So radiation hormesis says that if this is normal cancer risk, this is less cancer risk. With increasing dose, there will be an area where there's less cancer risk with radiation, up to a point that it becomes normal cancer risk, and then beyond which there's more cancer risk. The government right now ascribes to what's known as linear no threshold model, which means there's no safe level of radiation. So there's a lot of proponents to and for both of these, but right now the government ascribes to the linear no threshold model. So evidence for and against radiation hormesis: airline crews exposed to higher doses of cosmic radiation due to altitude show no overall increase in cancer. All those things. There's no chromosomal damage was detectable in animals with high radiation counts surviving Chernobyl. Evidence against radiation hormesis: pilots are more prone to brain, rectal, and prostate cancers. So you have those two different things competing with each other. So right now, just remember, linear no threshold is what you should remember, and especially for ALARA. You don't want to go around and go, hey, I'm getting radiation, I'm getting something good. Okay, not yet. Okay. So what is stochastic and what is non-stochastic? Stochastic effects are characterized by three qualities. They occur randomly or by chance. They're among both exposed and non-exposed populations, like cancer, genetic effects, etc. And the exposure increases the probability of the effect. So all these cancers that have happened to people, could it be from radiation? Maybe. Could it be from other things? Maybe. So that's what stochastic is. Non-stochastic is there must be a minimum dose before the effect is observed. An increase in dose results in an increase in magnitude of the effect. There's a definite cause and effect relationship. So a radiation burn from a prolonged interventional procedure, those things are stochastic. Sorry, those things are non-stochastic. So, radiation units. Between the time that radium was discovered and the Rankine unit was accepted, there were at least 50 different types of radiation units. I won't go into all this stuff, but so it was really hard to define what radiation is. We still have the SI units and the British system units right now that we use. So you have the Rankine, the Rad, Rem, and Curie. These are all the old system. The Rankine is a unit of exposure in air. The Rad is the radiation absorbed dose in material. Rem is Rankine equivalent man or biological damage. And the Curie is a unit of radioactivity. I'm going to go into this a little bit more in detail because it's tough to put you to sleep, yes. So what is the Rankine? The Rankine is the exposure in air. This is what we measure the Geiger counter with, okay? So the exposure measures the strength of radiation field at a point in time, point away from the source in air. So we measure this and we say, okay, this is so many millirem. So it's Rankine or millirankine. Rad is what is absorbed by the person. So Rad and gray is the absorbed dose. It's the amount of energy the ionizing radiation imparts to a given mass of matter. So that's what Rad means, radiation absorbed dose. In the SI units, it's gray. So you give in your reports to interventional how many grays of radiation that were given. The sievert is a biological effect of that radiation with that matter. So the sievert is the dose equivalent, and for the dose equivalent for gammas, X-rays, and betas, you multiply by a quality factor. And for gammas, alphas, and betas, and X-rays, the quality factor is 1. So basically the sievert and the gray, or the rad and the rem, for all intents and purposes is the same. So if you give one gray, it'll be the same as one sievert. If you give an alpha agent, you have to multiply by 20. That's the quality factor. So the quality factor for an alpha radiation will be 20, so you'd multiply it by that much. So that's the difference in energy that's imparted by an alpha versus the others. These are the conversions. At some point, you'll have to mug this up. Just remember, rad, rem, curie are the standard units, and the SI units are gray, sieverts, and becquerels. Maximum yearly dose, this is the ALARA that we've talked about. What can you get in terms of occupational exposure? That's 5,000 millirem or 5 rem per year. Whole body, the skin can receive 50,000. The eyes can receive 15, and that may be reduced in the near future. Dose to the embryo or fetus for an occupational worker is 500 versus 5,000. So if you're pregnant and you're a radiation worker, your maximum exposure drops down to 500 for the 9 months of pregnancy. General public is even less. They can only receive 100 millirem per year. So if you're in a radiation area, you have to prove that people walking through your hall only receive less than 100 millirem. So nuclear medicine places typically will have radiation badges and all that stuck on the wall just to make sure that general public is not receiving more than 100. So the ALARA concept, there are ALARA trigger levels also, and they go off of the maximum yearly dose. For the whole body, the ALARA level 1 is 125. That is per quarter of the maximum yearly dose. So if you divide 5,000 by 4, it's 1,250, and 1/10 of that is 125. So the other thing you have to know is if you're a nuclear worker, your maximum yearly dose is defined by NRC, which is 5,000. If you're a radiation worker using X-rays only, you're under the auspices of OSHA, which is not 5,000 per year, it's 1,250 per quarter. So that's the maximum you can receive per quarter. So for doing the interventionals and all that, just remember this is your limits, 125 per quarter. That's your level, ALARA level. Your maximum yearly, quarterly will be 1,250. Okay? If you're working in both, NRC takes jurisdiction. Okay. Also, this is something that's very important for you guys to understand. Back in 1980, the total dose of the US population for radiation was this, okay? The maximum amount of radiation a person would receive was from radon. Well, where do they get radon? Radon typically builds up as a radioactive gas in usually basements, especially in the north, and in building structures in the south, etc. So radon was the main source of radiation for a lot of people back in the 80s. And you can see medical X-rays was only 11%. Nuclear medicine was 4% back in 1980. Fast forward to 2006. This is radon. Much less than this. So radon is this much. CT is more than both nuclear medicine and medical X-rays combined at that time. So just CT. Nuclear medicine, interventional, conventional radiology for all. Look at the massive amount of increase we've had for the average population. So just remember that when you order tests and all, just remember there's a lot of this going on. And there is, Joint Commission has issued a Sentinel Event Alert, number 47, which describes the increasing number of radiation given to the public by medical procedures is getting to a critical level. So just remember that. What's happening in 2016? It's not out yet, so it's going to be a lot more. So that being said, the extremity radiographs are very low, less than 1 millirem. Chest X-rays about 10 millirem, mammograms about 20. CT scan gets about 1,000 millirems or 10 millisieverts. C-spine 44. Equivalent exposures, a pilot flying from New York to Athens will get about 420 rem, which is about half of a CT scan. Chicago to San Francisco, even less than that. Pi Ala mode is equivalent to about 35 millirem also. So just remember, in your flights, you will get some radiation. The number of CTs that people do have become astronomical. So that's something to just bear in mind as you go in the future.
You don't want to be a fat pilot getting a CT scan?
No. So this is my last slide, actually, and this is just an amazing thing that I like to go through. This is just a radiation dose equivalent chart. If you sleep next to somebody, you're going to be getting about 0.05 microsieverts. No one took my banana. So, smart radiologist here. All right. So, an arm X-ray is about 1 microsievert. A dental X-ray is about 5 microsieverts. The background dose received by an average person over one normal day is about 10 microsieverts. That's an airplane flight from New York to Los Angeles. You change units. All of that equals one green thing. The extra dose to Tokyo in the weeks following Fukushima was about 40 millisieverts. Living in a stone or brick or concrete building. So if you go to Utah and you go to live in an adobe house, you will be getting radiation from the walls there, okay? Average total dose to people in 3 Mile Island, living within 10 miles of 3 Mile Island, was about 80 microsieverts. Total dose received to the Fukushima town hall after over 2 weeks following the accident was about 100 microsieverts. The EPA yearly release limit for a nuclear power plant is 250 microsieverts. So nuclear power plants do release some radiation. Just remember that if you decide to live near one. And actually, last year it was an interesting thing that happened out somewhere in Missouri or so. They found like 1,000 dead starlings next to the nuclear power plant, so they had to do an emergency shutdown of the power plant. Turns out they were poisoned by a nearby farmer, but they weren't sure whether the birds were killed by the radiation, so they had to shut down the whole power plant and do an investigation. So, typical dose over 2 weeks in Fukushima is about 1 millisievert. A head CT is 2 millisieverts. This is the maximum yearly permitted to all radiation workers. This is a CT chest. Dose from spending 1 hour at the grounds of Chernobyl in 2010. So you would get 1 hour, you get about a CT scan in Chernobyl if you spent it for 1 hour there. And then larger doses, this is what a fatal dose would be. 8 sieverts. Okay, I think that was my last slide. And we're done. Any questions?
When you talk about counts in a photon multiplier device, in a gamma camera, what is counts? When they say counts, I just heard that term the other day.
In the Geiger counter or the photomultiplier tube in the camera?
I think it means the PMT. Count is just
The PMT.
I think it's the photon multiplier.
Yeah.
Scintillation.
Yeah.
Scintillation.
So inside the inside the crystal here, you get about 200,000 scintillations per minute for any study that we do. So if we give 25 millicuries of technetium for a cardiac study, put them under the camera, that area, this much by this much, gets about 250,000 counts per minute. And we image for over 20 minutes, so we get millions and millions of counts. So
So a count is an electric impulse?
yes, it's an electric impulse from the scintillation.
Camera hits the crystal.
That's a count.
Yeah.
You go in there, you can hear it.
See, the photon comes, strikes here, interacts with the matter, and that is determined as a count. Okay? But as it goes through, the pulse height analyzer, this thing here, is going to reject a lot of counts also. So we get 250,000 accepted beats, accepted counts. We may have 500,000 rejected counts from scatter and all that. Remember I showed you this, okay? The camera is picking up this window here, but also all of these counts are presenting to the crystal. So we may have millions of counts per minute, but we only accept the 250,000 inside that narrow window. Okay. So it's equivalent to one disintegration of a photon, or one interaction of that photon with the crystal that we're counting.
I guess the more counts, the better quality.
Yeah.
Yes, yes,
Images.
yes.
And more ding 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 ding. Ding ding ding.
You can go up to a certain point, but after a certain point, the crystals will have a dead time where they need to recharge. If you get to that point and they can't recharge, they can't send out another spark. So then too much counts is really too much counts is bad. And so you want to be in a sweet spot. Okay. Thank you.